is our first Good System Smart Cities Consortium lightning talk for the fall 2023 semester. We appreciate you attending. Today we will hear from Naveen Sudharsan. He is, I'll do a little about you that you sent over. He is a postdoctoral fellow in the Department of Earth and Planetary Sciences at the Jackson School of Geosciences here at UT. He has a PhD from the Indian Institute of Technology, Bombay, in environmental science and engineering. His research focused on heat waves and extreme precipitation events. His current research interests include mechanisms, observations, attribution, and projections of hydrometeorological extremes. So we can hear a little bit more from him. The floor is yours, Naveen. Thank you.
Hi. Thank you for the introduction. So let me add something. So I'm working with Dr. Niyogi and Dr. Yang in Jackson School. So here I'm working in the extremes, that is heat waves, hurricanes, and precipitation. So let me share my screen. Yeah, can you please enable? Can you see my screen? Yes, okay. So we are all in the midst of heat waves. So heat risk, I think heat risk is one of the hot topic now. So this is one of the works we have done here we started it from last January. So in heat risk mapping, we are coming with a new methodology that is totally non-parametric. So let me move into it. Okay, so you know that global warming is happening. And along with this global warming, intensity of heat waves, its duration and frequency is also increasing. So that brings into a point that we should consider intensity, duration, and frequency at the same time to understand heat waves comprehensively. If you're doing it with just one component, that is the intensity or just the duration or the frequency, that doesn't bring the full picture. So, yeah. So first of all, let me introduce an index. This is the Universal Thermal Climate Index. So we use this index to do the risk analysis because we know that it's just not the temperature that impacts human beings. And here in this particular index, we have air temperature, radiation, humidity, wind, along with a physiological and cloth model. So these scientists have run several simulations using this physiological and clothing model. So they bring up with an empirical equation because you may not be able to do these simulations all the time when you forecast something. So they come up with an empirical equation that feeds in just air temperature, radiation, humidity, and wind. So it's a big equation that's a six-degree polynomial. So I'm not showing it over here. So, and you can see this chart. So this is how they classify the heat stress. And this is in degrees Celsius. So for the point like 38 degrees Celsius is like 100 Fahrenheit. So in our study, we were just looking at these two categories. That is the very strong heat stress and extreme heat stress. So we have gone for 38 degrees Celsius and above. That is more than 100 Fahrenheit in our study. And for this, we first calculated the hazard. So for the hazard, we have used a different approach for heat waves. That is, we gone for a block maxima approach. where we have calculated the intensity and duration in such a way that a heat wave of 1 day in a year is like the maximum intensity of that year. And we went through like 2 consecutive days, 3 consecutive days, up to 10 consecutive days. So we are looking at 10 data points in a year. And then we moved on to see the joint probability. So we used kernel density estimation. And using kernel density estimations, we got the CDFs. Using these CDFs, we have come up with the intensity duration frequency curves. These intensity duration frequency curves um, shows the non-occurrence probability, and use we converted it to occurrence probability, and this occurrence probability we take it as the hazard. That is, frequency is the hazard here, and we used intensity and duration for calculating it. So moving on, then we need vulnerability. So I know there's a lot of equations. I'll just explain it simply. So it is basically a linear programming. So we have an optimization problem over here, and we have some constraints. So we have used two different methods, that is the CCR and BCC method. You can see what is CCR and BCC. So these two methods are most commonly used. And DEA is a management tool, and it is totally non-parametric, where you should not be giving any parameter into it, but it will automatically calculate the weights for each parameter. And for the analysis, vulnerability analysis, what we did is that we have gone through the US census, and we have taken 41 different criterions from that. So out of this 41, we have identified that 35 of them are sensitive parameters, and then 6 are adaptive parameters. So we have gone through PCA, that is principal component analysis, and reduced this number using PCAs for each, like for the sensitive and for the adaptive. And then we fed this sensitive parameters and adaptive parameters into this DEA approach, and we have got efficiency for each unit. Here, we have gone for the unit as county level. So for each county, we are getting an efficiency number. So converting it like 1 minus efficiency is taken as vulnerability. So we got a comparative vulnerability for each county for the CONUS, that's contiguous United States. So from these, we found that there is hazard for each county, and we have vulnerability for each county. So we use the product approach for risk, that is hazard, vulnerability, and exposure, the product of hazard, vulnerability, and exposure. So we went with a simple approach for the exposure, that is, we have taken exposure as the population for each, the population ratio for each counties as the exposure. So going into the results, this shows the hazard map for US, and this is for like more than 38 degrees Celsius of UTCI, and at least 3 days, at least 3 continuous days of that particular temperature. So in the case of hazard, what we have done is that we have gone for an AND approach, whereas there is another approach called OR approach. So here we are showing the AND hazard, where if you have a Venn diagram, then you do Venn diagram, the one is intensity and one is duration, then what is coming in the intersection, that is what is shown over here. So I think you are all familiar with this, that this particular area is much hotter than the other part. So we have a high hazard over this area. And then we went on to see what's happening with the vulnerability. So vulnerability is based on the effectiveness in which it can handle the hazard. So uh, we have gone through and we have got uh, comparative values for each counties. So you can see that this part is the most vulnerable. If there is high hazard, then that is disaster. So if you come to somewhere here, you can see that the uh, vulnerability is very less, and if there is hazardous events, still they can manage. So looking at this, we can understand that uh, which area should be focused more. So this is for the second methodology, and we compared these two maps, and we found that it shows almost the same results. And as BCC is more advanced than the CCR method, we went with BCC method. So this is the combination of vulnerability and hazard, and you can see that these areas are vulnerable but doesn't have much hazard. And when it comes to these areas, it is high hazard and high vulnerability. And so these areas which has high vulnerability and high hazard should be considered more when you make the policies. And this is the hazard map which involves the exposure as well. So here we are showing the product of vulnerability, hazard, and the exposure. So you can see that the red color shows the high risk areas, and this white shows the almost a white shows the least risk areas. And uh, so this is how these emergency activations happened in last 30 days. So if you look at it, and we know that last 30 days were very hot. So if you look at it, it almost coordinates with what we have in the risk map. So we assume that, and our methodology is correct. And we don't have a long-term data. If we have a long-term data, we could have compared it with it. So because the last 30 days doesn't show the hottest days for all the regions. And so if we come to the takeaways from these presentations are to introduce you UTCI and how important it is to use a index to understand the heat risk rather than just going with air temperature or any single variate. Instead, you should be always going with the combination of air temperature, humidity, radiation, and wind. Whereas in this particular model, we had a cloth model as well as a physiological model that shows the human metabolism. So this particular model is considered as the best suited for anything that's related to human health. And here we show a new methodology for developing heat risk maps. Yeah, thank you. So if you have anything to ask me, so you can either send it through my email or you can ask it here.
Thank you. I appreciate you taking a few minutes to discuss some of that. I have a question, but I can certainly let other folks speak first if anyone else would like to jump in. And if not, we can start over here.
Yeah.
All right. Yeah. Going back to the heat vulnerability and hazard map, the blue and red with the diamonds, does that sort of take into account population or whether people sort of like live in these areas? I noticed a lot of the scariest, darkest places, like just from personal experience, seem to be like Inland Empire area and out in like in California and I can't remember the name of the desert out there, but not a ton of population. Does this sort of take into account where people live?
Actually, in vulnerability analysis, we are not looking into the population, but we are looking into something like whatever parameters uh, that can be sensitive or adaptive to heat waves or heat hazards. So we have taken like people living alone, people having age greater than 65, less than 5 years old. All these parameters we have considered in this. So it shows the comparative result with all the counties in US. So if you are comparing with any part of the world, this can be used because when you consider something, if you are considering the whole world at a time, then you can compare. Otherwise, you can't compare it with it. So whatever units you have used in this, only those units can be compared.
Okay, I understand. That makes a little more sense now to me. Thank you. I appreciate it.
Yeah, thank you. Thank you for the, sorry. Oh, uh, could you hear my voice?
Yeah.
Oh, thank you. Thank you for the presentation. Yeah, I really appreciate it. I'm Yefu Chen. Actually, I'm a research assistant at the Urban Information Lab. And I do have a questions about some things, the things you present. First, I have to say that is really impressive. But I want to say, so you mentioned that when you're trying to build the CCR and ECC, you are using
Yeah.
the linear equations. Why don't you, since currently we do have kind of like emerging technology and non-linear relationship, why don't you using kind of non-linear equations in this situation?
We were looking into it in such a way that we thought we will find the we will go with a non-parametric approach where we will get the parameters from the data itself. So we thought that data envelopment analysis will be the best.
Okay, cool. Yeah, that makes sense. For the second one about the EMS activation,
Yeah.
I do have some similar feelings with Kana saying that there could be some areas that you mentioned that should be the priority place to take a look at. However, that place, well, the population and other things may not be that critical. I will take the Travis County as a sample. If you are familiar with Travis County, and you can compare that the surrounding county, the county surrounding Travis County is kind of much higher than the average, while in the
Yeah.
Travis County it's just like a zero or much lower than the average. So I will say that could be a little bit interesting for me to take a further look at, like what caused this situation. Maybe Travis is the most urbanized area in the metropolitan area, or whether that could be the one explanation to that. And also, I am thinking because the CDC do have different disaster distribution data, and if you can combine this kind of disease distribution, that you can combine this kind of disease distribution, for example, like the obesities and also other disease in your vulnerability research, I will say that could be much more helpful. Because
Yeah, that will be
people,
helpful.
yeah, because people from different population is one thing, but also like there could be more accurate risk population we can use for the vulnerability analysis. That will be my suggestion.
Yeah. So that will be useful. But during the summer, I had an intern, so we were trying to get the disease data, but it was very tough to get, and yeah, we couldn't do much in that. So
Yeah,
that's the problem.
I understand. Yeah, that could be an issue. And
I
also
think we all
about
understand.
yeah. And also the third thing, but definitely the last step, it's not a question but a comment saying that I'm not familiar about the data you use, but whether you are going to consider about some like the canopies for like a kind of a measurement saying that people have some shelter for to avoid the heat So what do you plan to do that, or
No, actually, in the vulnerability, if we have the data, we can add that. But what happened is that in census data, we don't have anything like that.
Oh.
So what we did was that how many people are not having houses, like mobile house, those who are using mobile homes, those things are added in it. And those and the homeless is also number of homeless people is also added.
yeah, that's a nice answer. Thank you again. Thank you so much.